Hello friends, in this lecture we will discuss about the mechanics of metal cutting. So before going to start, let us know what is mechanics of the metal cutting. So we can say that the current analysis is based on merchant thin shear plane model considering the minimum energy, and the model is applicable at very high cutting speed which are generally practiced in production is the known as mechanics of metal cutting. So in this one, which we are generally we have to practice in the production, and the object is prepared after the moving the cutting tool on the workpiece, and it will getting a desired shape is known as the metal cutting for the required purpose. So here we are looking in this figure. From the figure we can see that it is the relationship of orthogonal cutting in practice while turning a tube from the end. So here the cutting tool is moving on the workpiece, and the workpiece is fixed at the left shelf, and cutting tool is moving on the workpiece, and the strain gauge to measure the forces on the workpiece, how much force is applying, and how much we have to provide the fit rate, and cutting cutting forces, and similarly the axis of rotation along the uh, cutting tool. So these are the figures with the orthogonal cutting in the regular practice, and in tabular specimen we can see the front view of this object, and this is the side view of this object. So from the figure we can easily understand the concept of the orthogonal cutting. Now further, if we have to move, so some assumptions we have to follow, that is the tool is perfectly sharp. Your tool should be perfectly sharp, because if the tool will not sharp, with the proper cutting of the workpiece will not find. So the tool is perfectly sharp and has no contact along the clearance face. Second one is the surface where shear is occurring in a plane, and the third one is the cutting edge is a straight line extending perpendicular to the direction of the motion, and it generates a plane surface. And further, the chip does not fall flow to either side or no side spread. The chip should be collected at the box chip box. Next one is the uncut chip thickness should be constant, and the width of the tool is greater than the width of the workpiece. Next one is the continuous chip produced without any build up edge area, and work move with a uniform velocity, and the stress on the shear plane are uniformly distributed. So these are the main assumptions for the orthogonal cutting. Now further, after that we will see the main components of the forces that will be acting during this orthogonal cutting. So here we can see that some forces are acting. Horizontal force is acting, vertical force is acting. Means if you are looking in this figure, the force, the force FB is the force perpendicular. This is the force FB perpendicular to the primary tool motion, that is known as the thrust force. Second one is the Fs is the force along the shear plane. This is the force that is acting at the along the shear plane. Now, what is Ns? Ns here, Ns is the force normal to the shear plane, and F is the force frictional force along the neck face. This is the frictional force that is acting on the along the neck face. Now, capital N, here N is the normal force perpendicular to the neck face. So these are the various forces acting on the workpiece with the when the tool is moving on an object, and the chip is forming. Now, uh, after that, if we are looking at the properly, so when the chip is isolated as a free body as shown in figure, So we need to consider only two forces, the force between the tool face and the chip R, and the force between the workpiece and the chip along the shear plane. That is, if you are assuming R dash, it should be in equilibrium. So in isolated condition, we can say that force between the tool face and the chip R should be equal to the workpiece and the chip along the shear plane R dash. That should be in equilibrium. Now, if you are further looking in this figure, it is possible to represent all these forces be acting at the tool point in place of their actual point of action. By doing so, it is possible to construct a cutting force circle that is shown in figure, and which is often called merchant circle. This is known as the merchant circle diagram, and it is a simple exercise to derive the various relationship among the forces. So we will make some construction in this figure, and from this figure we can find some equations that will be the forces injecting in this horizontal and vertical direction, and we are resolving or splitting this figure into two parts. uh, Part of the merchant cutting force diagram will be separated into two parts, that is the uh, merchant cutting force diagram. And if you are looking in this figure, uh, we are resolving the forces in the along the shear horizontal plane and vertical plane. So here the force F, that is friction force along the rake face, is equal to Fh cos phi minus Fb sin phi. This is the equation number first. And further, if you are looking ns the force normal to the shear plane, if you are resolving and rearranging this term, so we will get the equation Fs is equals to ns is equals to Fs tan phi plus beta minus alpha. This is the equation for the normal force to the shear plane. Now, if we are moving further looking and observing the from the equation of second and third, from the figure second and third, what we are getting. So from there we will get the equation for the friction. Here from the figure we can see that this is the equation for the friction, and F is equals to Fh sin alpha plus Fb cos alpha, and N is equals to Fh cos alpha minus Fb sin alpha. These are the forces, frictional force along the rake face. Now, if mu is the coefficient of friction along the rake face, then mu is equals to tan beta, and F by N. This is the ratio of the frictional force along the rake face by normal force perpendicular to the rake face, and we can write here the value of F and N from the above equation. F is equals to Fv plus fh tan alpha by fh minus fb tan alpha, right? So from there you will get the equation for the coefficient of friction, where beta is the friction angle and phi is the shear angle. Now this friction is not similar to usually sliding case, since f and n are not uniformly distributed over the sliding area. So this aspect is discussed in further. Now the area of the shear plane should be given. As the area of the shear plane is equal to b into t by sin phi. B the width of the chip and t the thickness, and phi sin phi is the angle. Now the shear force is given in this figure. Fs is equal to tau into as. If you are finding the shear force, so we have to multiply with tau into as. As we found from the previous equation, that is bt by sin phi, and this equation will be put in the equation number 2.8. So from there we will get the equation for the shear force, where tau is the mean shear stress in the shear plane, and B the width of the cut, and T the uncut chip thickness. Now from there we will get the normal force, mean normal stress in the shear plane. Sigma is equals to ns by as, or ns we can write here sigma into as. We will cross multiply this equation. So from there we will get the value of ns is the sigma into bt by sin phi. Sigma, we will put the value of ns in that equation, and we will get the normal shear force, value of normal shear force from this equation. Now, further, if we are moving, so we will see that how we have to find the value of horizontal force and the vertical force. So, from this equation, we have to resolve this force into two components. First one is the horizontal component and the vertical component. The force will be resolved into Fs cos alpha plus Ns sin alpha. If we are writing the vertical force, so it will be Ns cos phi minus Fs sin phi from the given figure. So from there, if we are rearranging and substituting the all values, we will get fh equals to fs into cos phi plus sin phi tan into phi plus beta minus alpha. This will give you the equation number 2.12, and vertical force will give you the fs into cos phi tan phi plus beta minus alpha minus sin phi. So after rearranging this term, so we will get the horizontal force fs is equals to fs cos alpha minus beta by cos phi plus beta minus alpha. So after rearranging this term, we will get the horizontal force, and after rearranging this term, we will get fh is equals to tau bt cos beta minus alpha by sin phi I into cos phi plus beta minus alpha, and vertical force is the tau bt into sin beta minus alpha by sin phi I cos phi plus beta minus alpha. From the previous equation, if you are substituting all these values, we will get the value of the horizontal force. This is the cutting force, and the vertical forces. Now, if we are considering the merchant, that tau would have the value of yield stress for the work material, and that mu would have the usual value of any dry sliding fixture. So we have to determine the value of phi. So for the purpose of determining the value of phi, we have to assume that the minimum energy is applied in metal cutting, so that the deformation process adjusts instead to a minimum energy condition. So we have to differentiate in this equation 2.15 with respect to the phi. So we will get tau beta into cos beta minus alpha into cos 2 phi plus beta minus alpha by sin square phi into cos square phi plus beta minus alpha. This will give you the equation number 2.17. Now, if we are taking the maximum minimum energy for considering the uh, metal cutting process, so we will get a cos into 2 phi plus beta minus alpha, and 2 phi plus beta minus alpha is equal to pi by 2. We can write here because cos 0 is equal to pi by 2. Now from there we will get the value of phi is equal to pi by 4 minus half beta minus alpha. This will give the equation number 2.20. Now if we are substituting back, we can find that fh equals to 2 tau bt cot 5, and fv, that is the vertical force, tau bt into cot square 5 minus 1. Now further, if you are moving, so this will give the we will get the figure, and observing from this figure orthogonal cutting with shear plane. So from this figure we can see that the uh, minimum energy principle through appearing is not supported by evidence. So next it is assumes that beta and alpha are constant with respect to phi, with respect to this angle phi, but later studies on metal cutting have shown that at least beta is dependent on phi. Beta is dependent on phi. So this is connecting only steady state operation, but under dynamic condition alpha also varies. Here alpha will also vary under the dynamic condition, and from the experiment it was found that this equation is not valid. We will see more about the shear angle relationship later. If you are performing the experiment is not valid, so determine the shear angle experimentally. We have to stop the cutting process and study the zone with the help of microscope or a photograph. So alternately, we can also derive a relationship from the geometry of chip formation that is shown in this figure, and from there we will get the from the figure from this figure the value of T, chip thickness T is equals to AB sin phi, and TC the AB cos phi minus alpha. So from there we will get the two equations, two more equations. If we are assuming that uh, it is a cutting process and study the zone with the help of a microscope or a photograph. Now under the dynamic condition, now if we are taking the ratio of this value, so we will get the chip thickness ratio R, average chip thickness TC is equals to TL by LC, and from there we will get the relationship L is equals to pi into D. So I hope that you all have understood the content of the today lecture, and after doing this one we will get one more relationship TL, and from the velocity relationship in orthogonal cutting we will get the value of R here is equals to R is equals to, if we are considering the value of R is equals to, we will get a T by TC, chip thickness ratio T by TC, and if we are resolving and putting the value of T by TC, from there we will get the value of tan phi is equals to, here phi angle is there, that tan phi is equals to R cos phi, tan phi is equals to R cos phi by 1 minus R sin alpha. So after putting the value we will get the relationship tan TC is equals to TL by LC, right? So I hope that you all have understood the today's lecture, content of the today's lecture. Further we will continue with the relationship of the stress strain rate and the next strain angle, shear angle relationship, and we will do one more numerical related to this topic. So I am closing this this content for the today lecture. Next we will meet, right? So this is the equation for the tan phi. If we are putting the value of R is equal to T by T side T by TC, we will get the tan phi is equal to R cos phi by 1 minus R sin phi. So I'm uh, I'm I am closing this uh, I will today lecture. Further we will continue with the next topic.